So yes, welcome everyone. My name is Egill Fridgeirsson. I'm a postdoc here at the Department of Medical Informatics at the Erasmus University Medical Center in Rotterdam. And I'm gonna briefly talk about my recent JAMIA publication called Comparing Penalization Methods for Linear Models on Large Observational Health Data. So I'm gonna wind straight to the motivation for this work. So the lasso or L1 logistic regression is a heavily used penalized regression model on large observational health data. It's a method that performs regularizations and feature selection at the same time. So it shrinks coefficients towards zero, and some of them are shrunk completely to zero. And it has, on our type of data, it has very strong predictive capabilities. But at least in the literature, there have been a few weaknesses accounted. So, for example, if you have a group of features with very high pairwise correlations between the features in the group, lasso will select one feature from this group as a representative for the whole group. And further, it's not a stable feature selector. So if you change the data distribution a tiny bit, like with a different sample or bootstrapping or cross-validation, the final model you will get will be very different. But lasso has been, there are like 30 years almost now since the method was first published, and various related modeling methods have been published since then that deal with some of these weaknesses or have different trade-offs. So for example, for the group correlation, we can use elastic net, which selects the whole group instead of a representative. For the feature selection stability, there are adaptive regularization methods that penalize high coefficients less and small coefficients more, that are more stable in feature selection. But we are using these models, So yeah, so there's, when I started looking at the literature, I noticed there was a gap on these methods, in particular for large observational health data, and especially during external validation. So I saw a gap that would be easy to fill with some empirical research. So we are using these models for prediction. So I first want to get the terminology a bit straight. So we have a so-called index state when the patient enters our cohort, and we use all the features in an observation window that happens before the index state to predict an outcome during a time at risk after the index state. So in our case, the index date is the date that patients were diagnosed with major depressive disorder and they started drug treatment. The observation window was the last year before the index date. The time at risk is the year following the index state. And for the outcomes, we use 21 different adverse events. And this is a task that we've been using a lot in OHDSI for methodological work in prediction. Here is like a flowchart of the whole study. So in step one, we have our prediction problems. So for each database, there's a target and outcome pair. So we have 21 different outcomes. So we have 21 different prediction problems, and they all share the same target cohort. We extract our data from the database, and in this study, we included 5 databases: CCAE, MTCR, MTCD, Optum EHR, and Clinformatics. So these are 4 big US claims databases and 1 big US EHR database. And then we split our data into a training set and a test set. And on our training set, we develop our models. And in this study, what models we were comparing is, well, first of all, lasso or L1 logistic regression that penalizes by the absolute magnitude of the coefficient. Then we have ridge regression or L2 penalized logistic regression, which penalizes by the squared magnitude of the coefficient. Then there is elastic net, which is a combination of the previous 2. Then we had 2 adaptive methods, adaptive lasso and adaptive elastic net. And these are methods that Both work in a similar way as they penalize high coefficients less and low coefficients more. And then finally, but not least, we have two so-called L0 approximate L0 penalization methods, broken adaptive RIDS and iterative hard thresholding. And these methods work in a way that they don't penalize by the magnitude of the coefficient, they penalize by the number of non-zero coefficients that end up in the model. So they are quite different from the other ones. And once we have developed our models, we internally validate them on the separate test set that we separated in the previous step. And to evaluate the model performance, we use a few kind of different metrics. So for discrimination, we use the area under the receiver operating characteristic curve, or the AUC. And this is a measure of of the ordering of how we order the risk predictions on the test set. So for the patients that experience the outcome, we want to predict higher risks than for the patients who don't experience the outcome. And if you get this order correct, the AUC is high. But then there's another metric called calibration, which is a metric of how precise your risk estimates are. So if you have a group of people and you predict that they have 20% risk of certain outcome, then you'd expect actually 20% of them to experience the outcome. So if these two numbers match, then you have good calibration. And then we also look at the model size and put that in perspective of the other two metrics. And then once we have internally validated our models, it's time to externally validate them. So we have 5 databases in our study. So we develop the model on one database, and then we externally validate them on the other 4. So just to get an idea of the scale here, in total, we developed 840 models on 7.8 million patients, and we perform exactly 3,360 external validations. So this produces a lot of results. Let's just went straight into those. So how we, I need to explain this figure a bit. So what we do is that we consider each prediction problem in each database as a kind of a competition. So, and we look at how the models rank up against each other. So on average, ElasticNet and Lasso, they are always like ranking high. So they are ranking best out of all these models. And the line here that connects them indicates that they are not statistically significantly different from each other. Ridge regression is third, and then the adaptive methods and then the L0 methods trail. But the difference here between the best ranked methods and the worst is about 2.8 percentage points AUC. So that, like, depending on your problem, that might be a lot or that might be not so much. But yeah, it always depends on your problem. And that's, so yeah, I'm sorry, the panel A is the internal performance and panel B is the external validation performance. So as you can see, the external discrimination performance is basically almost matching exactly the internal performance. So those models who perform well internally also perform well externally. And then if you look at the calibration, you see the story is a bit different. So we see here that the approximate L0 methods are the best in terms of internal calibration with the other methods following them. But when it comes to external calibration, that's always an issue because the outcome rate in the other databases might be different than the ones that you developed your model on. So it seems that there is no clear modeling method that's performing better than the other ones. And if we put this into perspective of the model size, so if we look at the two models that perform best in terms of discrimination, Lasso and ElasticNet, you see the median model size, so the final, the non-zero coefficients included in the model, plus the intercept, is 189. And for the ElasticNet, it's 245. So These models perform the same, but Lasso does it with about 30% less non-zero coefficients. Another thing to note in this picture is the very small model size of the L0 based methods. So you see here that iterative hard thresholding has 13 coefficients and broken adaptive grids 17. So these methods give models that are very small. And to conclude, Lasso and ElasticNet lead in AUC performance, but Lasso does it with smaller models. The L0 methods, or the approximate L0 methods, lead in internal calibration, and the L0 methods give by far the smallest models with median sizes less than 20 coefficients. So you could truly call these data-driven parsimonious models. For example, if you take broken adaptive grids, is on average 2.5 percentage points worse than Lasso in the AUC for the internal validation, but it uses only the 8% of the coefficient that Lasso has. So you could say it's more bang for your buck in a way. And of course, this work would not have been possible without all my co-authors. I want to thank them especially. And yeah, you can scan the QR code if you're quick enough to read the paper, or otherwise I'll be happy to answer your questions in the chat. Thank you.